Welcome to a closer look at Gibbs free energy. Gibbs free energy is the energy associated with a chemical reaction that can be used to do work. The first law of thermodynamics tells us that the amount of energy in the universe is constant. Energy can be converted from one form to another, but it can never be created or destroyed. Energy takes on many different forms. When your car runs, it produces mechanical energy, or actually, when you run, you produce mechanical energy. There's electrical energy, which is delivered to our homes from power companies. There's light energy, which can be in the form of visible light, radio waves, or gamma radiation, to name a few. There's heat or thermal energy from the sun, fire, and even the earth itself. And there's chemical energy. Every molecule has bonds that store chemical energy. But it turns out that all these forms of energy may not be equally useful to us. For example, if you don't have electricity in your home, you can't generate it by riding a bicycle around your house. Or if you have cold hands or feet, you can't fill your hands with salt or some other chemical and hope that the energy from their bonds is going to warm you up. So some forms of energy are more useful than other forms. Every time energy gets transferred or transformed into another form of energy, it becomes less useful. That's related to entropy, represented with a symbol of S. Entropy is the measure of the spreading out or dispersal of energy as it gets used, which makes it less useful to us. It happens like this. The electric company generates concentrated energy that they send to our homes and businesses. We use that electricity to light our houses, wash clothes, operate our refrigerators, and so forth. And because of the conservation of energy, none of the energy goes away, even though we are using it. But after that electrical energy is used, it exists in different forms. Some of the energy has been transformed into light energy, some into heat energy, and some into mechanical energy. So even though the total amount of energy remains the same, it's now dispersed or spread out into other forms of energy that are not as useful. Scientists use a term called Gibbs free energy, which is designated by the symbol G, to estimate the energy that's actually available to do work, useful energy. And the mathematical equation that describes Gibbs free energy is shown right here. Again, G is the free energy or Gibbs free energy. Delta H is enthalpy change, which we can think of as the heat of the reaction. Delta S is the entropy change, or dispersal or spreading out of energy that we just discussed. T is temperature, which in this equation must be in units of Kelvin. So tuck that into your memory. We'll be using it later on. So now we have an equation that tells us about the amount of useful energy. But what are we going to use it for? The change in Gibbs free energy during a process, delta G, tells us whether or not that process will be spontaneous. A spontaneous process will occur without outside intervention. For example, if you leave an iron nail outside, it may start out shiny, but it would eventually rust, which is a spontaneous process. It would not require any outside intervention. But the rust on a nail like this one will never go away on its own. It's not spontaneous. You'd have to put energy in to remove the rust. It's the same thing with chemical reactions. If they have free energy left over after the reaction, or energy available to do work, that means the process will occur spontaneously. Spontaneous doesn't have anything to do with speed, though. Something can be spontaneous and very slow, even occurring over a period of years. The change in Gibbs free energy, delta G, allows us to predict whether or not the process will be spontaneous. If delta G is negative, the process will be spontaneous and there will be leftover energy that could be used to do work. A negative or exothermic change in enthalpy, delta H, and a positive change in entropy, delta S, will contribute to a spontaneous reaction. If delta G is positive, the process will not occur spontaneously. It would require an energy input for it to occur. A positive or endothermic change in enthalpy, delta H, and a negative change in entropy, delta S, will contribute to a non-spontaneous reaction. For example, the decomposition reaction that causes our automobile airbags to inflate during a collision is a non-spontaneous reaction. However, the mechanical energy provided during a collision provides enough energy to trigger a sensor that sends an electric signal. That ignites and then initiates the reaction for the decomposition to occur and the airbag to inflate. Now let's look at a calculation involving Gibbs free energy for a chemical process, the burning of propane. This problem asks us to calculate the change in Gibbs free energy for the reaction listed below with the following temperature, enthalpy, and entropy measurement at 298 Kelvin, given that the change in enthalpy is equal to negative 2,219.9 kilojoules and the change in entropy is equal to negative 0.374 kilojoules per Kelvin. We will use our equation again that says that the change in free energy, or Gibbs free energy, is equal to the change in the enthalpy minus the Kelvin temperature times the change in entropy. And when we plug in the given values for the entropy change and the enthalpy change into our Gibbs free energy equation, you have negative 2,219.9 minus the product of 298 and negative 0.374, which is negative 111.452. And when you do the math, you find that the change in free energy for this reaction is negative 2,110 kilojoules after rounding to the correct significant figures. This negative value for the change in free energy tells us that this reaction would proceed spontaneously the way that it's written. The next problem involves the conversion of ATP to ADP, which is how our bodies generate energy. This reaction occurs at 293 Kelvin. Remember, when we are working with Gibbs free energy, you work in temperature units of Kelvin. Here's the problem. If the change in enthalpy, or heat of reaction, delta H, for this process has a value of 19,070 calories, and the change in entropy, delta S of the reaction, is 90 calories per Kelvin, calculate the change in Gibbs free energy, delta G, for the reaction. Notice that we are measuring this reaction in calories rather than kilojoules. Even though it is not an SI unit, calories are often used to measure energy in living cells. 1 lab calorie, spelled with a lowercase c, is equal to 4.18 joules. We also want to determine whether the reaction is spontaneous under these conditions. Remember to start with the Gibbs free energy equation shown here. Plug in the numbers that were given in the problem. The enthalpy of reaction, or heat of reaction, is 19,070 calories, and the temperature at which this reaction occurs is 293 Kelvin. The entropy change is 90 calories per Kelvin. When you plug those values, you have 90,070 minus the product of 293 and 90, which is 26,370. And when you do the math, you find out that the free energy change of this process under these conditions is negative 7,300 calories. Delta G in this case is less than 0, or negative. So what does that mean? It means that this reaction is spontaneous, and thank goodness, because we need that energy as we convert ATP to ADP, or we wouldn't be able to live. Now here's a calculation for you to try. It's the same reaction we just discussed, but this time let's lower the temperature. Let's say you put your body in an extremely cold room and cooled it from 293 Kelvin to 193 Kelvin, which is about 80 degrees below 0 Celsius or minus 112 degrees Fahrenheit. That's unrealistic, but let's use it just to show you the effect that it would have on the spontaneity and free energy of the conversion of ATP to ADP. So use the same equation as we used in the first example, but plug in the new temperature, 193 Kelvin, and see how that affects the delta G value. Press pause while you're doing the calculation, and then hit play when you're ready to see if you got it right. Let's check your answer. By simply lowering the temperature from 293 Kelvin to 193 Kelvin, the delta G, or free energy value, goes from negative to positive. If you got that, you got it right. Remember that a positive delta G, positive free energy value, means non-spontaneous. So that's telling us that that same process that was spontaneous at 293 Kelvin is now non-spontaneous at 193 Kelvin. It's not going to happen unless we give it some extra energy. And that extra energy would be to take you out of that freezer we've put you in and warm you up so that your ATP can once again convert to ADP and give you energy. So now you know more about Gibbs free energy and what it shows us about useful energy. For more chemistry matters, go to our homepage, where the entire series is available to you.